The shape of the universe has always been a point of speculation. But what if I told you that we could figure it out by using a string and the universe? Let's consider the same for a planet. We make a loop on the surface of the planet and try to gather it in. If we were able to do so, then the planet would be a sphere, and if there were gaps, then the string would get snagged. A property called connectedness helped us understand the shape of the universe. But where did connectedness come from? In 1736, Leonhard Euler encountered the puzzle of the 7 bridges of Knigsberg. A path had to be made without crossing any bridge twice. Euler found that such a path was not possible, and so developed the geometry of connections, topology. Euler came up with a formula where the vertices minus edges plus faces of any polyhedral figure was always 2. The same can be done for a sphere by dividing it in any way we want. But for a torus, it is 0. If we morph the torus into the shape that is shown, the Euler characteristic remains the same, that is 0. This characteristic is represented by the Greek letter chi, which does not change if we morph a shape into another and is hence called an invariant. 2 minus 2g is a formula that can be used to determine the chi for any torus, where g is the genus or the number of holes. August Mobius extended Euler's formula to come up with a shape that is non-orientable. Yes, it is the Mobius band. It is the simplest 2D surface that can be created in 3D space. When an ant walks the length of the Mobius band, the left and the right sides of the paper are reversed, and it has to take 2 rounds in order to reach where it began. Further on, 2 Mobius bands can be connected to form a Klein bottle. Another non-orientable shape, it can only exist in 4 dimensions. Since the 4th dimension is time, we cannot see it all at once. You might be wondering as to where all this is useful. For that, let's see what a vector field is first. For a sphere, 2 zero vector fields of vortices are formed, one at each pole. If it turns anti-clockwise, the index is +1 and it is -1 when it goes clockwise. The sum of the vortices formed is surprisingly the Euler characteristic of the shape. Topology applied to physics has led to dramatic developments in the study of new phases of matter. Ordinary phase transition, say, is when ice changes to water. A topological phase transition involves small vortices which are invariants. When excited, the vortices suddenly move away from each other, causing the phase transition. Integers describe the properties of topological matter. They do not change by decimals. This makes them very sturdy and are not affected by any impurities or disorders. Hence, they hold a lot of promise for next generation computing devices. Nowadays, scientists have discovered several unexpected topological states of matter even in ordinary 3D materials. We may soon have a new periodic table altogether, or might just discover time travel by studying Mobius band.